Thanks, everyone. So it's quite a pleasure to talk about research on safeguarding machine learning. As a brief introduction of myself, my name is Xiaochen. I'm a lecturer in math and stats. My background is always in statistical science, but my research is quite borderline between statistics and machine learning. I also do lots of applications in healthcare. So today I'll talk about safeguarding machine learning. And to start with, I will talk about adversarial attack. I'm not sure how many of you have heard about it, but this is a quite famous example of pig can fly. So what do we mean by it? So on the left, so on the left, we have an image of pig. And if you send it to any image recognition system, it will tell you this is a pig. It's also quite confident in the prediction, say I'm 91% confident this is a pig. But now what's going on is now add a bit of noise. So this noise is not random. It might look like random to us, but it's not a random noise. You add a small magnitude of 0.05 times this like really strange noise. And then to us, I probably just turn her. And to us, this image is still a pig, right? So we think it's a pig. But if we send it to machine learning algorithm, it says this is an airplane. And it's very confident, 99% is airplane. So this is the famous example of pig can fly. We have more realistic or physical attack that could happen in real life, which is a big concern. So on the left, we have the traffic sign. So it's a stop sign, quite clear, but now we have some gravity, like the black and white block. And now this image system will say, this is speed limit of 45. You can just go ahead. And on the right is similar case. We have three images. The first image is US character, Kylie Jenner, I don't know. So many actress. But now you give her a really strange glass, or this colorful glass, and now the system will recognize it as another actress and then see traces. So that's a really concern because we are going to an era of autonomous driving face recognition system, but this type of attack can make the whole system fail. So that's a really big concern. But how do we get this type of error? Like how do we get this type of attack? So this is very simple to do it, actually. So if you think about traditional machine learning, what we do is we normally have some input data X and Y. X is our image, Y is our label, and we have a neural network, can be written like F with a parameter W. So what we do in machine learning, normally we just optimize our parameter to minimize the loss function. We want our cross-entropy loss to be small, our mean square error to be small. But to generate an adversarial example, all we need to do is we add this term delta x. That's a very small perturbation. We just constrain this perturbation to have an LP norm smaller than epsilon. So it's a very tiny amount of perturbation. We add it to the original input. And now we want to optimize this delta x to make this loss as big as possible. So if we can find such delta x, that means our loss become huge, and then that make the whole system fail. And to defend it, it's also quite straightforward. You just do the min-max problem. So you retrain your parameters. You train your parameters to minimize this max loss function. So it's a very simple step. You just maximize the perturbation and then minimize this adversarial loss. So that's a quite straightforward thing to do. But there are two issues. So one thing is, in the previous slide, we need to know what is our neural network. We also need to know what is the parameter in the network. But if we are attacking a system, say, built by Google or Microsoft, they are not going to give us all their model. So how can an attacker attack it if they don't know this architecture? That is the one question. Is in most of the time, attacker will attack whatever system they don't have in advance, but it can still be successful. So how do we know? How can we achieve this attack given we know nothing? And the second thing is, even if we train the model to be robust, but we change the attack way, we change it into another attack system, our model also fail quite often. So is there a way we can be absolutely sure that our model is robust to this type of attack? So that is the two key questions I'm going to talk about in the next 10 minutes. So the first work I'm going to talk about is how we can generate this black box attack. So let's look at this problem again. So on the left, we have the image of a pig. And then we know what is architecture of neural network, what is the parameter, and then we can generate a tag to make it an airplane. But in reality, normally we don't know the parameter, we don't know the architecture. That's a black box scenario. And what we want to achieve in this case is let's develop something based on a substitute model. So although we don't know what is the black box model, we can try to find something similar. So for example, if we are having a computation image recognition system by VGG, we can then use a substitute model of a ResNet. So is there a way we can train a model on a substitute model and make sure this attack can transfer to our target model? So this property is called adversarial transferability. So that means any adversarial examples crafted for one model can successfully attack any other models that might differ quite dramatically. So how can we achieve this property? So if we can have such attack that can be used to attack any system, but how do we achieve it? So let's think about this property. So this property is very similar to generalization we have done in machine learning for ages. So what we do in machine learning is we have some training data. We want a method to perform well on this training data, and then we use this system to some test data. We want to make sure the performance perform relatively equally. So we are looking for generalization across data. But now what we want to do is we want to have this generalization across models. So we have one model, it works well on this model, and then it can generalize to other models. So they have some similar things in common. And in data generalization, we have lots of techniques like data augmentation. If you have lots of data, your model might generalize better. Or you can have ensemble model. So you have lots of different models and then combine them to make them powerful. So is there a way we can use these two ideas but make it apply to the model perspective? So we want to build a data augmentation and ensemble to train different substitute model. But if we train different substitute model, that could be time consuming. We don't want to train hundreds of deep neural network. That's too much and costs too much time. So in our work, what we do is we introduce a Bayesian formulation. So by doing so, we can think as if we draw random sample from this Bayesian distribution, that is equivalent to a tag ensemble of infinite many deep neural networks. So forgive me, there are a bit of math in this slide, so I'll just jump into details. So first, let's recap what is Bayesian model averaging. So assume we have a prior distribution over the parameters, and then by using Bayes' theorem, we can get the posterior distribution. So we have the probability of weight given our data set is proportional to the joint likelihood times the prior. And then when we make a prediction, then our probability of y, our response given our data set and a training data set D, is equals to y given x and particular parameter w times its posterior. And then you can integrate over all the parameters. So that is Bayesian model averaging. And then when we generate a tag, as said, we just optimize this function. So we add a bit of perturbation to make the correct probability to be as small as possible. And then we can do it iteratively. So instead of generating only one delta x, we can do it in multiple steps. So we can, up to the current step, we have already generated some perturbation, we can add a little bit extra. So you do it in multiple times. So in Bayesian formulation, we just want to combine these two equations. So what we do is we just introduce prior to parameters and input. So we combine these two equations. So what we do is have this integration part to replace this formula. So you just plug in the first line into the second line. And now what we have is we introduce a prior distribution on the parameter and introduce a prior distribution on the input. So we just make them, instead of this deterministic, we add some distribution to the parameter and input. And this integration is quite costly to do it, so we just draw some random sample. So we'll draw M sample from the distribution of W, draw S sample from the distribution of input. So, and then we can just do the normal gradient descent to optimize it. And if we want to improve it, we can just improve the distribution. So because our prior distribution reflects our belief in the system, so we can just improve it. So by the simplest we do is we don't know anything. We just assume they are normal distribution. So our prior distribution is just at the mean value of our current parameters with some random noise. Our input perturbation is a mean zero Gaussian distribution with some variance sigma squared. So that's the simplest thing. We know nothing. We just assume they are all normal distribution. Or we can fine tune it. So by fine-tuning, what means is we try to learn the parameter W to minimize the loss function. Or we can use more advanced technique like stochastic weighted average Gaussian. So you just accumulate all the parameters, and then this gives you a more powerful attack. So this is part of the experiment result. So what we do is our substrate model, the model we have right now is a ResNet 50, and we use it to attack a different type of models. So for example, we can use it to attack VGG19 inception ResNet 152. So to people who are less familiar, they are just different architecture for image recognition. So we train on ResNet and attack different architectures. And the gray box, the one on the leftmost, that is the default so I would say classical method, so iteratively attack approach. And then the blue box is when we start to add the prior to the weight parameter, but we didn't tune anything. And then the orange one, the third leftmost one, is we also add randomness to our input data. And then the last one is we start to fine tuning. So we see once we start to fine tuning, we'll get higher and higher attack rate. So on average, what we achieve now is you train attack on one model, it can successfully attack on average like 75% on all other models. Okay, so we also did lots of experiments on combining different methods. So for each role, like MI, FG, DI2, FG, they are just different attack methods. So you can always combine the method to improve their performance. So just a quick summary. So what we did in this case is we just introduced a Bayesian formulation to adversarial attack, and this can be treated as you attacking an infinite many neural networks. And if it's possible, if you can afford the computation cost, then you can do a bit of fine-tuning to improve the success rate. Okay, so we talk about the attack side, and then the next thing is how we define the system. And this leads to how we can make sure we achieve the certified robustness. And what I'm going to talk about is in the frame of metric learning. So metric learning might be new to some of you, most of you, but I'll just briefly explain the idea of metric learning. All it means is you learn a distinct metric from the data. So for example, we have some image of dog. So if your task is differentiate the breed of dog, you will say, okay, the left 4 images are Pomeranian, I can't remember the name of dog, and then the right 4 are poodle dogs. So that is one way you see the difference between this image, or you can separate them by color. So the top row are all brown color, then the bottom row are all white. So based on your task, you can use different ways to classify them. So metric learning means you just learn a different metric that which is suitable for your task. And the way we learn it is we just learn a matrix. So just ignore the formula. All we need to learn, in this case, the parameter is a matrix. So this matrix is positive semi-definite. And because this nice property, we can think as the data doing a linear projection. And then in that linear space, you do your classification. And the way we train this matrix, so you can just think matrix M is a parameter. So the way we treat it is we just minimize some loss function and add a bit of regularization. So we want to make sure it's not overfit to the training data. It can be used in quite different scenarios, like open set classification. So you have some photos in your training data, and then you want to use the classifier for some other photo you never seen before. That's open set classification, or it can be used for information retrieval, different tasks. So how can we achieve the certified robustness in this context? So let's first look at what is certified robust. That means if a model is said to be R-robust, that means whenever you add perturbation, so you add perturbation delta, as long as your perturbation is in this range, its magnitude is within this range, you can't successfully attack the system. So that is this definition. So that means if you can think of you have a ball of some perturbation, if it jumps within this ball, then you can never get success. So that's a certified robust. How can we find this perturbation in the case of metric learning? So we start with a simple 3 points. So that's, you can think as xi is our data point, the point we are trying to classify. And then we are using one nearest neighbor as classifier. So in that case, xj is its nearest neighbor, and xl is a nearest neighbor from different class. So basically what you want to know is xi close to xj or is this close to xl? And in metric learning, once you learn the metric, that is a linear projection, you can project it into the space on the right. So if the metric is good, then that means you have all similar points, all the yellow circle points to be close, and then the red square should be far apart because it's from different class. That's the idea of metric learning. And if the method is not robust, what will happen is I just slightly change my data point xi. I perturb it to xi prime. It just move a little bit. But then once you learn the metric, the point becomes really far away. So Lxi prime lies on the wrong side of the decision boundary. It becomes closer to the red point. So that is what happens. Your method is not robust at all. So you change the input a bit, but the decision change at all. So how can we find a margin which guarantee our system is always robust? So what we do is we need to find the point xi minimum. That point is quite close to the original point, but at the same time, it's always correctly classified. So on the left, this point should be close to the original point, but once you learn the metric, it should be also still on the correct decision. And if you put these two ideas into an optimization problem, that means your new point should be closest to the original data point in the original space, at the same time lie on the decision boundary in the feature space. And if we use 1 year's neighbor, we know the decision boundary is simply the perpendicular bisector. So it's in the middle of this, it's in the middle of this 2 point and also perpendicular to the middle point. So that is the 1 year's neighbor classified. And then mathematically, we can write it as this equation. And if there's a closed form solution, you solve it and you get your final result. And then you know what is xi at min, and then you count the distance between xi and this point. You get the margin. But there's nothing. So it's all nice, clean. So we don't need to worry about approximation or whatever. And next thing is we find this margin. We want our model to be robust. That means we want this margin to be as large as possible. So if this margin is large, that means any point within this circle is not going to be affected. So we just use perturbation loss, but the main part in this loss function is simply the hinge loss. So what that means is we want our margin to be larger than a value top. So you just only need to worry about this part. And we can maximize this loss function, and that can give us a robust method. We show this loss function can be combined with different metric learning methods. And also it can be proved theoretically that by improving your robustness, you also help with generalization. You also get higher accuracy on clean data. And just as part of the experiments, the first one we test is an image data set, MLiS. So it's a handwritten digits from 0 to 9. And first we can look at the rightmost column, that's the margin. So by using our method, we see that our margin can become larger, like from 0.15 to 0.22. That's with when you combine it with the method LMN. But if you combine with other methods, you always see the margin become larger. And also we check the clean accuracy, the noise accuracy, they all become better. So just to summarize, in this work, we find an analytical form of adversarial example. So this is quite different from deep learning. In deep learning, we can't find such closed form solution. We also always need a bit of approximation. But in metric learning, it's really nice and neat. So you got a nice solution. And then we can use this margin idea to improve the robustness. Okay, so given we are in a machine learning in science conference, I just want to say a few words on where we can apply these techniques in other subjects. So in social science or maybe psychology, we do some survey. So once we have surveyed, all data collected are often categorical data. So you can have different movie genres, or you can have ordinal variables, like people giving you different opinions. So that type of data is quite common in social science. And a few issues is one possible issue is feature ambiguity. So what I mean is we give a rating of excellent or good, but no one can clearly define what it means by excellent or what is good. So there's no score to define the different boundary. And the second thing is maybe because privacy or ethical issue, normally the data set is quite small. So we can't collect lots of image as in training computation system. So to solve this problem, you can actually use the adversarial learning technique I just introduced before. But all you need to do is carefully design the perturbation set, so the one in the red. So I'm not going into detail, but I just want to show this framework can be used in other subjects as well. And also with the small sample size, once you train it, we will show that it also helps to reduce the requirement for sample size. I will just end my slide, talk about what is going on in the field, what is the future direction. It should be surprised, like everyone now start to work more on large language model. And in the large language model, you do an adversarial attack. There are a few challenges. The first thing is how do you define whether the model is success? Because in image recognition, you can just say, okay, it's classified correctly or incorrectly. But in large language model, we are generating tests. So we will say, okay, there are some unsafe contexts, like how to cook a drug. But how do you define whether this model is safe, whether this content is safe or not, unless you ask some human to do it? So there's no clear way to define what is the sex of adversarial attack. And also the other thing is how to optimize the model. So we normally use gradient descent to optimize the model, but then in image, all the data are continuous. But when we have the test data, they are all discrete distribution. So how you can optimize such attack is a hard issue. And because the first two haven't been solved yet, I think currently people are not working so much on defend. So normally it's attack first and then defend. So I think once we solve the first two problems, we might have a better strategy to defend large language model against these attacks. Okay, so I just finished my talk to thank my collaborator, Evan at ByteDance, and Xiaochen is the student who carried out the transferability work, and my supervisor at UCL. Thanks, everyone.
Thanks for the talk. Okay, we have 5 minutes for questions. I really like this whole approach that you're working on, but I found it interesting. Your Bayesian approach, does it only work for models which have the same architecture? Like if you have different numbers of weights, for example, in the target model, would that still work? It would still work.
Because we only train one model, so we only focus on one substitute model and make sure we optimize on that model. And once the optimal attack can be used to add any other attack, any other target.
And this Bayesian formulation, does it still make sense? Let's say you train on some, let's say something which is a purely convolutional neural network. Would it still make sense to try to attack a transformer in this Bayesian formulation where you have different weights? So the probability distribution, this posterior of your initial convolutional weights doesn't necessarily make sense mathematically in my head. Can you comment on that?
Most of the time, it's similar architecture. Say if it's a convolution network, you can use VGG to attack ResNet or wide ResNet. But if it's transformer, then you need to train a transformer backbone. So you can't use like a convolution to attack transformer. That's probably not work. But you can use, say, BERT model to attack other transformer-based architecture. Yeah, so it's not going to say generalize across very different architecture, but if they're fundamental idea, let's say they're all based on convolution or they are all based on transformer actor, then you just train one single model and then attack the other. And once your model gap become larger and larger, your success rate might become poor and poor.
Are there any? Thank you. First of all, are there any questions from the audience? If not, then I wanted to ask, sort of related to this. You mentioned about large language models that it's difficult to attack them because, first of all, it's hard to define what is a successful attack, and then also you mentioned that unlike images, they are not. It's not a continuous distribution that you're basically attacking. So what does that mean? Your perturbation is not continuous, or the target is not continuous, and how does this affect your overall approach, or how would one approach attacking such a like a large language model in general?
So your text is normally modeled as a discrete distribution, and then in that case, when you optimize it, you don't have that continuity. You can't use gradient descent to optimize that loss function. So you I think most of people are using some search algorithm to do the optimization. So it's not only with the perturbation range. Of course, that need to change to accommodate text, but the text distribution itself now is become district distribution, like binomial, whatever. No, sorry, nominomial or whatever distribution. And then when you try to optimize it, you can't use the first order gradient descent or quite common, say, Adam or whatever. So you need to use search algorithm that become much slower than the current way to attack it.
And my last question is somewhat related to Professor Hetherington's talk actually in the morning. If one wants to create robust machine learning algorithms that actually that work also in the field and not just in your testing environment, it seems like your approach would be relevant for that as well. Like with the example of the pig, because that could very well have been a picture of a different pig, but it was still misclassified. What would you say is the simplest method for a researcher who wants to improve the robustness of their own method? How can they borrow from your ideas of being robust against adversarial attacks for that sort of work?
Yeah, that makes sense. How to improve it? I think maybe the first starting point is to know how vulnerable is the method. Like, are your method really easily attacked? And if it is, then definitely improve it. And I don't think there's an easy way to solve it, but most of research in this area, we have open source code. So you can use classical method or more advanced method, but there should be some package available for you to just directly implement your method and then add maybe a loss function on the top of it.
And if you're just interested in finding out how vulnerable your method is it okay to just, for example, brute force sample different Gaussian noise and add it onto your image, or maybe delete, remove one pixel, set it to zeros? Is it enough to just test that way, or would you suggest going down the route of the adversarial attack that you suggested? So trying to maximize a loss, for example, and see how that can be done. What do you suggest?
Most of cases, Gaussian will not successfully attack it. So if you have at Gaussian, your method probably gonna perform still quite well. So I think adversarial is something really need careful design. But if your system is not worried about that at all, then you can just test with Gaussian. But if you think your system is going to use in a scenario where people will want to attack it, and then you do need like this type of method, because Gaussian, we tried it, normally it can't successfully attack the system.
So just random Gaussians aren't fine. Probably it needs to be a specific type of.
Yes, because it's only change a specific pixel. It's not like random pixel you pick out. It's only that particular pixel make the whole difference. Because so the way you think it is, you have a loss. Sorry. So the why it is so sensitive is our neural network is a really complex model. It gives you a loss function being really sharp. And then if your decision is just at that sharp corner, the decision will change. But it's very hard to find where is that corner. So if you random pick a pixel, it might be in a smooth part of the loss function. You need to exactly find the peak of that loss function to make the attack. So that's why, like, normally random sampling probably can't attack the system.
Okay. There's one question. Could we? Yes, thank you. And then that will be the last question.
Yeah, it's sort of related to what you were just saying. And this might be my deep lack of understanding of how it works, but is there a way that if it's some very specific noise map that changes this from a decision of a pig to an aircraft, right? Could I not just take my image of a pig, add lots and lots of different examples of noise, and see if it still predicts as a pig? And then if there's an adversarial attack, because I've added that noise already, it's kind of cancelled out the effect of the adversarial attack, and see if it's still predicting a 99% of the time, then it was probably a picture of a pig. that make sense?
Yeah, so I think that one, so you have an image, you add lots of Gaussian noise, keep training it, getting multiple models. That's a really good way to defend against attack. But that's you can't guarantee you that there is an attack that can success. So really depends on if you are an attacker who just want to break Google system, then you will try really hard to find that particular point to break the whole system. If you train multiple models, that means attacker will take a longer time, but you still have the risk that at a certain point you can find a pixel that make the whole system fail.
Thank you. Are you going to be around? Okay, then if there's any more questions, please find Xiaochen, and thank you again for your talk.